So, last week we started talking about the different segments in circles that can be formed by circles. So, one of the different segments that we talked about was two different chords. All right. So, just to recap, all right, if we have two minor arcs that are congruent, what's true about the chords that make them? So two arcs are congruent. What is true about the chords that make them? So just for reference, okay, I have a circle. Let's call this AB, CB. All right. If arcs AB and CT are congruent, what's true about the chords? They're also congruent. All right. So if you have two congruent arcs, the chords that they're between are also congruent, and vice versa. If the two chords are congruent, that means their arcs of the form are congruent. All right. So if I have, say, these two chords, so this EF, GH. Let's say that these chords like this. What's true about those chords? So this is the center C. I'm bisected. They're what? So what do these two lines show? That the chords are what to the center? Equal distance. So they're equal distance from the center. That means that they are what? Congruent. All right. So these chords are congruent. And the last one, I have a radius and a chord. All right. And it's perpendicular. So the intersection of perpendicular angle, what's true? What bisects what? Right, the radius bisects the chord. So that means it cuts into two equal pieces. It also does what? Doesn't just bisect the chord, it bisects the arc. The arc also bisects. All right. So those are the three that we talked about on Friday of last week, just as a quick recap. Now we're going to do some more today. All right. So with the next journal entry 6.5, there's only two theorems for this one. All right. The first theorem is if a line is tangent to a circle, what does it mean for it to be tangent? What's a tangent line? It only hits the circle once at one point. Then it is perpendicular to the radius drawn to the point of tangency. So in other words, if I drew this line out a bit more, this is a tangent line because it only hits one time. All right. Now, this right here is my radius. So this is R. This line is T. So, yes.
Your paper's what? Oh, this is the one from last week. So, if we have the point of tangency, all right, that means that where they intersect right here is a right angle. So, guys, I'm on the journal that you grabbed last week. Now, since that's true, that means that this triangle is a what? It's a right triangle. So, what do you think you typically have to do here? So, let's say I was given side A, B, and C, and I wanted to find the length of side C. What would I use if I knew the lengths of side A and B? Pythagorean theorem. So, this becomes a right triangle because of that, which means somewhere in there'd be some Pythagorean theorem. Now, the other theorem is if two segments from the same exterior points are tangent to a circle, then they are congruent. So, in other words, if you have two tangent lines that intersect at the same point outside the circle, so see how these two intersect at the same point? And they're both tangent, they only cross at one point. That means that both of these segments are congruent. Now, to expand upon that a little bit, if I drew a radii from each of the points of tangency, what happens to those angles right here and here? Based off of our last theorem, they're now what? So I now connected a radius to a point of tangency. So that means that this angle is what? It's a right angle. So both of those angles will form right angles. So if I draw this, all right, now that line in the middle would be the hypotenuse. And since it's the same, that means they share them. So that segment is congruent to itself. So technically, we have congruent triangles by hypotenuse leg because the hypotenuse is congruent and two of its legs are congruent. So that means that both of these triangles, that means both of those triangles would be congruent to each other. Hint, hint, wink, wink. So to make a note, it conforms two congruent triangles. And not only are they congruent, they're also right triangles. All right, let's look at some examples. These are fairly quick. So, first example on the left. In a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn from the point of tangency. So, what it's asking here is to kind of fill in the blanks. What line is tangent here? Not quite. So, you may not know this, but when we talk about lines, all right, you can label them with 2 points that are on the line, which is totally fine. But if they give you like a little lowercase letter, so if they give you like a little lowercase letter around the line, that's the other name for the line. So this line's actually named line L. But you could also name it line YT, XT, YX, whatever, as long as it's between 2 points on the line. But since they gave us that little L, we're going to use that. So is tangent to the circle if and only if line L again is perpendicular to what segment? So this line here has to be perpendicular to what segment? ST. Has to be perpendicular to the radius ST. So the angle for STX, which is right here, is 90 degrees. Now, what's the point of tangency? What letter? So in other words, what's the point that the tangent line hits the circle? T. All right, so for that one, we're just kind of restating what they told us on the previous page. Now, for the other one, if two segments from the same exterior point are tangent to a circle, then they are congruent. So if QP and RP are tangent to the circle C, so lines QP, so right here, and RP are tangent to circle C, then what's true about those two segments? So what's true about segment QP and segment RP? What's true about them? They're congruent. So what's true about them? They are congruent because they form at the same outside point. So QP is congruent to RP. So again, we were pretty much just restating what they already told us in the previous page. Any questions so far? Now, below is where they're actually having us ask some questions about this. So all 6 of these questions are going to be using this diagram over here, and they should overlap. All right. So, actually, no, they don't overlap, but you'll see in a second. All right. So, first off, they want us to find the measure of angle BCM. So, I start at B, I go to C, and then I go to M. So, the angle it's talking about is right here. What's that angle measure? 90 degrees. Why? Because it's a radius intersecting the what? The point of tangency. So this is definitely a tangent line right here. It only hits at one point. And BC is the radius. So that means that this angle right here is 90 degrees. Now, it wants us to find the length of CM if CM is equal to 5x minus 9 and MZ is equal to x plus 7. So they said that CM is equal to 5x minus 9, MZ is equal to x plus 7. Now, what's true about CM and MZ before we even start anything? Someone besides Jasmine. They're congruent. Why? Why are they congruent? Where do they both meet? Right, they meet at point M. So they both meet at point M, which is the same exterior point, meaning they're congruent to each other. So if CM is congruent to MZ, how do I set up my equation to solve? Set them equal to each other, solve for x. So I have 5x minus 9 is equal to x plus 7. Subtract the x to both sides. That goes away. I get 4x minus 9 is equal to positive 7. Add 9. 4x is equal to 16. Divide by 4. X is equal to 4. Now, that's not my answer. Why? That's for the length of CM. Now, we can plug back into either CM or we can plug back into MZ. Why can I plug back into MZ as well as CM? They're congruent. So I'm going to plug this 4, just so we know, back into CM specifically. So I have 5 times 4 minus 9, 20 minus 9. So CM is equal to 11. So what's MZ equal to? 11. All right. Now, we're going to find the length of EM if CM is equal to 12 and BC is equal to 5. So I'm just going to label it. Now, like I said, these questions don't connect to each other. All right. So in the previous problem, we said that CM is equal to 11. Now they're saying CM is equal to 12. All right. These questions do not connect. We're just using the same diagram. All right. So I'm going to label this as 12 and BC as 5. And they want us to find EM. And by EM, I mean right here. So that green segment, that's what they want us to find. Now, before I can find EM, what would be the most sense to find first? Someone besides Jasmine. So I can't quite find EM right now, but I can find something that connects to it. I can find BM because we can use Pythagorean theorem. So I'm going to find BM first. So if this is A, B, and C, I would have 12 squared plus 5 squared is equal to C squared. So 144 plus 25 is equal to C squared. 169 is equal to C squared. Take a square root. 13 is equal to C, or BM. So if BM is 13, how do I find EM? So BM is made up of 2 segments, BE and EM. Do I know the length of BE? Are you sure? What is BE technically? What type of segment? It's a radius. Do I not know what the radius is? It's 5 because they already said up here that BC is 5. Well, is BC not also a radius? Yes, no, maybe? Yes. So that means BE is also 5. So what do you think EM is? 8. So you would do 13 minus 5. EM is equal to 8. So guys, that one, you actually had to think outside the box a little bit, but it wasn't really too far outside the box. You just had to know that a radius anywhere on the circle is the same length. Any questions on that one? All right. So if MBM is 60 degrees and CM is 13 square root 3, find the length of BC. All right. So we're completely disregarding everything we just talked about. Now, I'm going to erase some of this stuff just so we can see it better. If you already have it on your paper, that's fine. I'm just letting you know that I'm erasing it, but it is also captured in the video. All right. So for whatever reason, if you missed that part, it's captured in the video. Now, CBM is 60 degrees. So CBM, which is this angle right here, 60 degrees. CM is 13 square root 3. They want to know what BC is. Okay, so we talked briefly about this last week. We know that this angle is 90 degrees. That doesn't change. So that means this little angle right here is what? 30 degrees. So this is a right triangle, but it's also a special right triangle. All right. So here's my question to you. If this is a special right triangle, so I'm just going to give it a draw over here real quick. Right angle, 30, 60, B, C, M, 13 square root 3. Let's call this X. So if this is a right triangle, and it's a special right triangle, it's a 30, 60, 90 triangle. So remember, we talked about this briefly last week. It should be written down somewhere on that journal from last week. So remember, when we're talking about 30, 60, 90 triangle, we're talking about, and I'll draw it off to the side, we're talking about a triangle where the angle directly across from the 30 is the short leg, the angle across from the 60 is the long leg, angle across from the hypotenuse is the hypotenuse, or the side across, sorry. And if the short leg is a length of A, the long leg is a length of A times the square root of 3, and the hypotenuse is a length of 2 times A. So, the 13 square root of 3 is across from which angle? So it's diagonal to which angle? The 60. So it's considered which, what? The short leg, long leg, or hypotenuse? The long leg. So in other words, it's equal to A times square root 3. Now, BC or X is across from which angle? It's across from the which angle? 30. So that's my short leg, which is A. So if I'm going from A times square root of 3 to just A, how do I get there? So if I'm going from here to here, how do I get there? So this is the same thing as A times square root 3, and I want to get rid of the square root 3 to get to A. How do I get rid of it? What undoes multiplication? Division. Square root of 3 is just a number. We can easily divide it. So that's exactly what I'm going to do. I'm going to do 13 square root of 3 divided by the square root of 3 to give me BC. What happens to those two square root 3's? Don't they cancel each other out? They go bye-bye. So I'm left with what? 13. That's all I had to do. So like I said, guys, you need to know those 30, 60, 90s because it will come back to haunt you. All right? All right, let's do number 5. So I'm going to erase this again. Well, this is still a right angle. So BC is 12. BM is 20. So this entirety right here is 20. And they want us to find CM or X. So I'm automatically using what? What method? Pythagorean theorem. So how do I set it up? So I'm definitely using a squared plus b squared is equal to c squared. But how do I set it up using what I'm given? Right. 12 squared plus x squared or b squared, however you want to put it, is equal to 20 squared. And then we just solve for x. So I got 144 plus x squared is equal to 400, which is 20 squared. Subtract 144 to both sides. I get x squared is equal to 256. Does anyone know what the square root of 256 is off the top of their head? It's 16. So x is equal to 16, or that's also cm. I just want to see if y'all knew what it was off the top of your head. I knew what it was, but. All right, last one. So the length of XC, that's what they want us to find. If BM is 25 and ZM is 20. So let's look for a second. So they want the length of XE. So that's right here. If BM is 25 and ZM is 20. So let's come up with a plan of attack here. What's true about the segment XE? It's the what of the circle. So the segment XC is actually the what? It's the diameter. It's formed by two radiuses. So in reality, what do I actually need to find first? So I'm given this segment and this segment. So if I'm given the diameter is equal to what in terms of the radius? How do I get the diameter from the radius? I do what? Multiply the radius by 2. So it's twice the radius. Do I know how big the radius is? So do I know how big the radius is? Yes, no, maybe. Given the information that they gave me, do I know what the radius is? Not from previous questions. So we don't quite know what the radius is yet, but we can find it. So all we got is the hypotenuse of this triangle and one of the legs. We don't know what this radius is. So what we need to do first is find BZ. Because if we find BZ, we can multiply it by 2 to get XC. Because it doesn't matter which radius we find on this circle, as long as we find the radius. Because remember, any radii on the same circle is going to be congruent. So, again, we got Pythagorean theorem. So this will be 20 squared plus x squared is equal to 25 squared. So this will be 400 plus x squared is equal to 625. Subtract 400. X squared is equal to 225. Square root both sides. Anyone know what square root of 225 is off the top of their head? 15. So x is equal to 15. Now, that is the radius. So how do I find the diameter, or XE? If 15 is the radius, that means my diameter is 30. If I do 2 times 15, it's equal to 30. Any questions on that particular journal? All right, so go ahead and take your 5-minute break. Be back here by 12:10, and we're going to do that other one. So that other one's fairly quick.
So ready after? No. I'm not holding the ball. Awesome. Sure. What's up the Matthew? Shut up. This.
Guys, how about that third journal that you described? This last one's pretty quick.
Are we also doing next like packet too?
Packets just really practice. This time around.
You'll want to let
Well, most of the notes were in the journal anyway. The only thing that was packet.
What do you want to do?
All right, y'all, let's get back to it. So the last type of segments that we're going to talk about are more so special cases. Typically, these are intersecting chords. If you have two secant chords intersecting, and if you have a secant and a tangent chord intersecting. So far what we've talked about is chords that have not intersected, chords that have intersected with a radius. We've talked about two tangents that are intersecting. And we've talked about a radius and a tangent intersecting, but we haven't talked about these three types just yet. Now, the first one is just the intersecting chords. So if two chords intersect in a circle, then the products of the measures of the segments of the chords are equal. That's a mouthful, but let me explain what that means. All right. So technically speaking, what are my two chords here? So I have two chords on this circle. What are those two chords names? NW is one of them. What's the other one? KL. So NW is one chord, KL is the other one. All right. And what that means is if I go from N to E, let's call that A. From E to W, let's call that B. From K to E, let's call that C. And from E to L, let's call that D. All that's saying is that if we multiply the different pieces of each individual chord, it would equal the product of the pieces of the other chord. So it just means A times B is equal to C times D. So for example, like let's say that A was 2, B was 3, so D was 6 and C was 1. All right, we would have 2 times 3 is equal to 1 times 6. Is that not true? Yeah, 6 is equal to 6. That's all it's saying. They're proportional pretty much. All right. So if we look at the following example, all right, what are my two chord names here? So what are my two chords? So we have DB and we have CA. What are the two different parts? Let's call this point here F, all right, because the center is E. But let's call their intersecting point F. What is one part of DB? So if I cut DB into two pieces, what's the length of one piece? 6. So that would be from F to B, and that's 6. What's the other length? So we have the 6 here. What's this other length? X minus 1. So this would be FD, and that's X minus 1. Now, CA. What's the length of AE? Or AF, sorry. So what's the length of AF? 4. What's the length of FC? X plus 3. So if I'm solving for X using what we just did over here, how do I set up my equation? So to make it easier, let's label these. So let's say that 6 is A, X minus 1 is B, X 4 is C, and X plus 3 is D, all lowercase. So remember, we know that A times B is equal to C times D. In other words, 2 pieces of one chord multiplied together is congruent or equal to the product of the 2 pieces of the other chord. So how do I set up my equation using that piece of information? So guys, what did I do over here? So what did I do right here? So NW I broke up into 2 pieces, NE and EW. NE was 2, EW was 3. I multiplied them together, it got 6. KL could be split up into 2 pieces, KEEL. Multiply them together, 1 times 6 is 6. They have to be equal to each other. So I ask again, how do I set it up over here? Good. Right. Equal to 4 times X plus 3. Good. Yeah. So that is how we would set it up. All we do is multiply those 2 segment lengths together on each side of the equal sign. Remember, they have to be a part of the same chord for you to multiply them together. And then we can just solve. So we distribute on both sides. 6x minus 6 is equal to 4x plus 12. Subtract the variable to the other side. I get 2x minus 6 is equal to 12. Add 6. I get 2x is equal to 18. And then divide by 2. X is equal to what? 9. All right, so that's all you do with that segment. All right. Now, the next theorem deals with 2 secant lines or 2 secant segments. So if 2 secant segments are drawn to a circle from the same exterior point, so similar to the 2 tangents that we just dealt with, then the product of the measures of one secant segment and its external segment is equal to the product of the measures of the other segment and its external secant segment. So that's a whole lot of what they just said. But essentially, let me just break this down for you. So what they're saying is that the outer segment times the whole segment is equal to the outer segment times the whole. That still probably doesn't make sense, but let me explain. So if we look at the circle here, the whole secant segment goes from the outside point to its end point over here. So this is considered the whole. That's the entirety of the segment. So that's the whole. The outer segment is the part of the segment that's outside the circle. So S to E is the outer part of segment SC. And S to N is the outer part of SA. Now, we don't really care about this, but I'm just going to mention it anyway. The inner part is what's actually inside the circle. So EC is the inner, and A is the inner part of that segment. And we don't really care about these. All right. So in terms of the problem, we don't really care about those. Now, that being said, that means that if I multiply our outer SE and SN times the holes, which is SC and SA, they would be equal to each other. All right. That's what it's saying. It's saying that if you multiply the outer part of the segment of each secant segment times the whole length of its segment, of one of the segments, it'll be equal to the other segment with that same product. Now, that probably doesn't make a lot of sense, but once we put it into a example problem, it'll be a little bit easier to figure out. So let's look at this one. So it wants us to find OG, which is labeled X. So before you do anything, you need to label what your whole, your inner, and your outer is. And you can just do that using like O, I, and W. All right. So if I'm looking at segment OL, what is the length of my outer? Or which segment is my outer with what length? For segment OL, which part of OL is outside the circle? GL. So this is my outer, which means it's also 6. Which one's my inner for OL? OG. So OG is my inner, or let's call it I. Now, my whole is the entirety of OL. How can I find my whole? What will my whole be equal to? All right, we'll stick a pin in that and we'll come back to that. Look at LS. All right. Wait. It's what? Not quite. Not quite. You're on the right track, but you kind of derailed a little bit. So let's look at LS. That might give you an idea. All right. So what's my outer segment for LS? EL. So the 8. So right here, that's my outer. Which one's my inner? SE. So that's my inner. So what is the length of my whole if the inner is 18 and the outer is 8? So you have 2 pieces of the same segment. What do you have to do to find that total length? Combine it how? What operation? So if I have this whole segment and I cut it into 2 pieces, one piece is 18, the other piece is 8. What's the length of my whole segment? Or how do I find it? Come on, guys. I know it's Monday, but give me something. So you just add them together. So in other words, if you have a whole segment and it's cut into 2 pieces, one of the pieces is one length, the other piece is another length. You know the length of both pieces of the same segment. You just add them together. So this is equal to whatever 18 plus 8 is, which is 26. So coming back to the length of OL, what do you think it is? So using, say it, not 6x, but you're on the right track, x plus 6. So we add the two lengths together. It has a length of x and a length of 6, so x plus 6. Now we can set it up using our formula. So outer whole is equal to outer times whole. So using that piece of information, how do I set up my equation? So for OL, what's my outer? 6 times, what's my whole? Plus 6. All right. For SL, what's my outer? What's my whole? 26. And thus our equation is set up. So we distribute over here and we multiply over here. So this will be 6x plus 36 is equal to 208. All right. What's my next step? Subtract the 36 from both sides. I get 6x is equal to 172. Divide both sides by 6. And this will not be a nice number. But for time's sake, I'm just going to tell you. So OG, which is equal to X, is equal to 28.7. So you put 172 divided by 6, you get 28.7, approximately. It's like 28.666667, something like that. All right, any questions on that one? So it's not necessarily complicated. You just got to know how to break it down. All right. Now, the last theorem is very, very similar to the one we just talked about, but it deals with a tangent in a secant. So, a tangent segment and a secant segment are drawn to a circle from the same exterior point. The square of the measure of the tangent segment is equal to the product of the measures of the secant segment and its external secant segment. So again, mouthful, but all it's saying is that just like with the secant segment, if we label this the inner, this the outer, and this is the whole. Well, the tangent segment doesn't have an inner. It's all an outer and a whole. So in reality, the tangent segment, the whole entirety of the tangent segment is the outer and the whole. And we'll just call that A. All right. What I'm saying is that A squared, which is the entirety of the tangent, is equal to outer times the whole, which is your secant. So this right here is my tangent, comes from my tangent line. This part right here comes from my secant line. And again, it's because we have to count TR twice because it's still outer times whole. So it's still the exact same formula. But in this case, the tangent line is both the outer and the whole because it's both outside the circle and it's the full segment. All right, so we have to count it twice. Yeah. Oh, it's a T. It's a T. TR. And so that would be equal to WR times SR. So that's where they get the squared from. So in other words, we're still doing outer whole is equal to outer whole. All right. But in this case, the tangent line, it's kind of a double whammy. The tangent acts as both the outer and the whole, but you still have to count it twice. All right. So if we do this last problem fairly quickly, Which side is my tangent? Which segment? So AM is my tangent. I'm just going to put tan. Which side's my secant? MC is my secant. And they want us to find BC. So X. So let's go through and label. So for the tangent line, what's my outer? What's my whole? What's the length of my outer for the tangent? 10. What's the length of my whole for the tangent? 10. It's both. So this is both the outer and the whole. So in other words, when we multiply it, we're going to square 10. Now, which length is my outer for the secant segment? So with my secant segment, which segment length represents my outer? 6. Which one represents my inner? X. So what is the length of my whole? X plus 6. So if I set it up still using outer whole is equal to outer times whole, that means I'm doing 10 times 10 for my tangent, because again, it counts twice, is equal to 6 times x plus 6, because I'm doing my outer times my whole. So this would be the same thing as 10 squared is equal to 6 times x plus 6. And then I can start the solving process. So 10 squared is 100. Distribute. I get 6x plus 36. Subtract the 36 to both sides. Get 64 is equal to 6x. Divide by 6. Again, it's not a nice one, but it's equal to about 10.7. So that's the length of BC. Any questions on that part? All right, so let me ask you guys this. So the last thing we got to do is technically fill out the backside of your topic web from last week. So you know how you had the one with the angles on the front side? Well, the backside is the segments. So here's my question to you. I have the key already. So do you want to go through it as a class? Because it's basically just summing up what we just discussed. Or do you want me to post it in Canvas and you guys copy it on your own? Post in Canvas? All right, that's fine. So I'll post it in Canvas as soon as I get back to my desk. Go ahead and copy that on your own for like the last 30-ish minutes of class, as well as you should be able to finish that Delta math that I assigned on Friday. All right. Also, with the Delta maths, something I forgot to mention, since we're getting closer and closer to the EOC, I've started posting what I call